Hello everyone, my name is Arianne Barros and I would like to thank you for attending my presentation. So, this work is named Development of an Equation-Oriented Model Applied to a Hydrodesulfurization Process and is being developed at the Iridium Research Group from the Federal University of Campina Grande, with contributions of Code's Research Group from West Virginia University. So before I talk to you about the project itself, I would like to do a brief contextualization of the theme. The oil refinery is composed of many processes, which have the purpose of separating and converting crude oil into final products, as we can see on this simplified flowchart of the left side. One of the most relevant concerns of an oil refining process is achieving a high quality of their fluids. In this way, impurity removal and the maintenance of catalyst efficiency are key points to produce these fluids. Hydrotreating can be considered one of the most relevant processes in this context, and it can be defined as a set of reactions of petroleum fractions with hydrogen in the presence of a catalyst under controlled operating conditions. In these illustrations, it's possible to see in a didactic way how these reactions occur. An oil molecule contaminated with sulfur contacts a hydrogen molecule on the catalyst surface and suffering its connection break, producing two new components, a desulfurized oil molecule and a molecule of hydrogen sulfide. Some relevant information need to be considered to the model constellations. So HTT is extensively applied to remove impurities such as heteroatoms like sulfur, nitrogen, and oxygen. Also polynuclear aromatic and metal-containing compounds. According to the nature of the oil charged impurities, the hydrotreating process can be classified into different categories. The most common reactions occurring during hydrotreating are hydrodesulfurization, hydrodenitronization, hydrodeoxygenation, and hydrodearomatization. Among the oleolytic impurities, sulfur proves to be harmful because it is corrosive, increases the oil's polarity, causes color change of final products, and it is a contaminant to several catalysts in the refining process. There are many types of configurations of HTT reactor, depending on the feed characteristics. In general, this process occurs in trickle-bed reactors operating in one or more stages under high pressure. The trickle-bed reactor can operate with a concurrent downflow in a three-phase system: liquid feed, gas, hydrogen, and solid catalyst, as you can see in this picture. Although both liquid and gas phases flow through the reactor, the reactions occurs only in the liquid phase. For this work, we are considering that the reactor operates adiabatically and the reactions are extremely exothermic. The highly exothermic nature of the reactions leads the system to divide the total volume of the catalyst into beds to improve the process performance. That is, the number of catalytic reactor beds is defined based on the maximum temperature variation that each bed is capable to support. To maintain full activity and stability of the catalyst, it is necessary to maintain an adequate reaction temperature, carried out by cooling zones located between the beds, called quench zones. The reaction depends on a set of parameters, such as operating temperature, partial hydrogen pressure, and residence time, and all the set will define the unit severity. The concentration of impurities in the oil and the quality of the associated desired final product will define the treatment intensity and influence the overall performance of the process. One of the most relevant references for this work is the study developed by Professor Tavernar et al. 2020, which deals with a plug-flow HTT model developed to predict an industrial diesel hydrotreating reactor performance. Computational fluid dynamics and data of a real industrial plant have been used to validate the HDT model. In order to support and verify the plug flow assumption, it was used a CFD model in a 2D plane for the predictions of spatial gradients of the reactor variables. A zoom out on the left side, left reactor bed shown in the picture indicates that the sulfur content gradient is pronounced only in a very small close region close to the reactor wall. This fact confirms that the plug flow reactor model can be used without loss of information on the reactor predictions. This paper was considered most of the HTT reactions, gas leaked and liquid solid mass transfer, as well as the influence of catalyst deactivation and quantity zones. One of the most significant results obtained by Professor Tavernard's group was the verification of the catalyst deactivation model on the measured temperature and sulfur content in the inlet and outlet of HDT reactor over an industrial campaign, that is, 4 years of running time. For this presentation, we will present a part of the proposed model by Tavernard's group, focusing on the hydrodesulfurization process. This work's motivation is based on the development and customization of a reactional block on the AVIVA process simulation platform, based on the HTT model, focusing initially on the hydrodesulfurization process. In this first moment, we focused on implementing an equation-oriented model of an HDS reactor on the AVIVA process simulator. It is based on the initial part of Professor Tavernard's trickle-bed reactor. Then, such HDS block model will be used as the sub-model base for the second step that corresponds to a more detailed version of HDT trickle-bed reactor, where a set of typical reactions will be defined. This is a simplified flowchart that summarizes the most relevant information about the methodology used for such a block. These highlighted shapes correspond to a component lump block that will be presented in the poster session. Such a step will be used to connect the oil components to the HDS pseudo components and vice versa. Going back to the HDS block development, first of all, it is necessary to define the model inputs, such as reactor nominal conditions, component catalyst properties, besides all the information of the kinetics. This is the base for the mass transfer coefficients calculations and the solve of the needed balance equations to obtain the output concentration, temperature outlet, and components pressure. Before initiating the model implementation in the AVIVA process simulator platform, the model was simulated in MATLAB and validated with data experimental results. In the AVIVA simulator environment, a single block was initially created, containing all the information from the hydrodesulfurization process. After analyzing the data's results and consistency in such a block, it was decided to adapt the HDS model block using submodels, connectors, and functions similar to the PF reactor model available at the AVIVA process simulator platform. Here we can see the initial results that were obtained for this first developed structure. After that, some improvements have been made, and the results obtained were described as the expected behavior of literature, as we can see in the picture. We aim to develop the entire reaction section described by Tavernard et al. 2020 work. The final idea of the HDS process flowchart is this view on the canvas. That is, at the end of the implementation of all the beds, including the quench zones, the hydrodesulfurization block must be able to reproduce an industrial temperature and sulfur remove profile. Here we have some things that are under development on the HDS block, such as the evaluation of the differential equation set on the HDS reactor length, the structuration of connections between the reactor beds, the calculation of the oil properties, and the estimation of the sulfur content of the oil. Now, I would like to express our thanks to the partners responsible for the development of this work and to make all our communication platforms available for possible clarifications and contacts. Thank you all.